Uh, Good evening. Am I audible? I hope I am. Okay. I'll share my screen, then we'll start the session. I hope my screen is visible. So, welcome to problem solving session of environmental chemistry. This is week 5, I guess. So, week 6. So, we'll start the session now. I am Mansi Tripathi, TA for this particular course. So, we'll start the session. So, in this session, first I want you to understand about the equilibrium diagrams. Sun has taught this concept, but I want to go more into deep so that you can do it manually. So we'll start with that. Then we'll see what other things we can cover. Then we'll see the question answer for this particular week. So that will be relevant to this particular week. But the concepts are little older that I'm going to teach for now. Okay, so we'll start it. So equilibrium diagram. So equilibrium diagram of the acid-base equation problem is constructed by plotting the logarithmic plot of the concentration of each individual species versus pH. So equilibrium diagram I will say as ED. So it is nothing but a plot between log of concentration versus pH. Okay, so this is equilibrium diagram. So concentration of each individual species. If we say HCl, so the species can be H plus, it can be Cl minus, or HCl itself. So whatever the concentration of each species at a particular pH is there, that we can plot. So when we plot it in form of log, it is in the form of straight line. Or there will be some curves, but mostly it will be straight line. So it will be easier for us to understand that what is the concentration of that particular species. Okay. So what we will be plotting is number one, strong monoprotic acid, weak monoprotic acid, and weak diprotic acid. So we will study for these three type of acids, and accordingly other things can be prepared for even for 4H plus with acid with 4H, that also we can prepare, and we can prepare for alkaline compounds also. So this is the basic thing that we will discuss everything. So important thing for this type of graph is assumption. So what is the assumption in the such cases? Assumption is that the solution of acid in water is ideal. So when it is ideal, what will happen? The activity, okay, of any compound, let's say H, is equal to concentration. Okay, activity that is represented in curly brackets, which is equal to concentration. So we are considered the solution as ideal. So that is the only assumption we have. Now I will give you steps. What are the steps for drawing the diagram? So once you learn the steps, then after that, if any type of acid is given, you can easily draw equilibrium diagram. And from that equilibrium diagram, you can easily find out what is the pH at that particular point. So, okay. So first we will study about strong monoprotic acid. ED of strong monoprotic acid. So first step is write balanced chemical equation. So that is the first step in mostly in all kinds of problem. Write a balanced chemical equation. Okay. So when we use graphical technique, okay, the equilibrium diagram is all kinds of graphical technique. So we always assume for strong acid I'm saying, we always assume that ionization of all strong acids and bases uh, is complete. Okay, that what that means is if HA is there, it is being completely converted to H plus and A minus. So that thing is very important for strong acids and bases. Okay, this was the first step. So there is no reverse reaction. This is a reaction will go in forward direction. So write a balanced chemical equation in that term. If H2O is also there, like HCl is strong acid, right? But if I give 10 raised to power minus 8 HCl, at that time you have to write for equation for H2O also because it is very very dilute. So for H2O also we have to write and see it is not going in reverse direction. So this is what we assume for strong monoprotic acid. The next step is we have to write equilibrium constant expression. I will write for Kw. Here, if we will do for weak monoprotic acid, then Ka equation will also come. Okay, but this is strong acid, so Ka tends to infinity. So that is why that thing is not considered. Okay, everything is ionized. Okay, so that is why in case of strong monoprotic acids and all, only Kw is considered, Ka is not considered. The C point is write a mass balance relationship. We have to write a mass balance relationship which accounts for total mass of non-metal group. Okay, here this thing is important. We need to consider non-metal group. Okay, so what is non-metal group? When we write Ha, this thing is considered non-metal group. So we have to write total mass balance equation of this case. So, and this will only appear when there is complete ionization. Otherwise, we will get Ha also. But since we are considering complete ionization, this Ha won't come into picture. Okay, so Cut is equal to A negative. Okay, so these are, after that, what we have to do? So define the chemical species which exist in the system. Now we need to write all the species. Okay, so since this is strong acid, so what will be there? One will be there H plus, OH, because water we have to consider, and we will have A negative, right? Only these three things we will have. Now we have to develop, the next step is develop plotting equation. Okay, next step is to develop a plotting equation for all the steps, all the species that we have defined in D. Okay, so first is we have to write a balanced chemical equation. Then we have to write all the equilibrium constant involved. Since this is strong acid, only Kw will be there. Then we have to write the mass balance relationship of non-metal group. Okay, then we have to define all the species, and then for each species we have to write a plotting equation. Okay, so now let's write, if we want to write a plotting equation for A, let's write for A first. If we want to, and all the equation should be in terms of log, because this is graph between log concentration versus pH. So we want equilibrium diagram. So all these equations should be in the form of log. So for log A, what we have to do? Simple. This equation, put log both the sides. So log A is equal to log Ct. For A, it's done. So this is equation 1. Other things are also there in log, all the species. So we know H plus OH minus is equal to Kw. Putting log both sides, what will happen? Log H plus log OH minus is equal to log Kw. Okay, and what we can write? Log OH minus is equal to pH minus pKw. What is pH? Negative log of this. Just to make it negative, we will get log OH minus is equal to pH minus Kw. Okay. After doing all these things, we will be getting a set of equation. So now, for now, there is a procedure to derive the whole curve, whole this plot. But just remember few things. This is the plot. Okay, log Ct, log of species, any species versus pH. So two things you have to remember. Make a cross first. this cross will be H plus and this will be OH minus. So this will be common in all types of plot. Okay. Now what we found? Now H plus and OH are plotted. Only three things we had to plot, right? H plus, OH and A negative. Three things we had to plot. H plus and OH are plotted. Now next comes A negative. So what is A negative? A negative is equal to log Ct and Ct is total concentration. So whatever our total concentration is there, that is plotted. So this is, let us assume this point was Ct. So this is log Ct. Log Ct is equal to A, log A negative. So this was A negative. So all these things are plotted. So very simple. For example, if I give you to plot 10 raised to power minus 5 mole HCl, what we have to do? Simple. As I told you, this will be H plus, this will be H minus, and this will be Cl minus. And what will be this point? This point will be minus 5. Simple. Okay. This is H plus, OH minus, Cl negative. I hope you understood. And whatever this power is there, at that point only you have to make the line. Okay. I hope you understood for monoprotic strong acid. Now we will study about monoprotic weak acid. Here everything will be same, only we will get a Ka value. And here now complete ionization won't be there. Next comes weak monoprotic acid. So first step was equilibrium equation, balanced chemical equation. So what will be the balanced equation? If we have weak monoprotic acid as Ha, it will give H plus plus A minus, because this is weak, so that is why we will get both the signs here, forward reaction and backward reaction. Second, for water we have to write, and water will also be in both the directions, H plus plus OH minus. Now second step was equilibrium constant expression. So Ka is equal to H plus A minus Ha, and Kw we know H plus OH minus. Now third step was species. So what will be the species? H plus OH minus A negative. Apart from that, we will have Ha also, because it won't be completely ionized. So you remember, right, how to make diagram for OH and H plus? Just cross. Okay. Then we have two more things here. The dynamics will change. There are two more things, one more thing to design, and A negative dynamics will change a little. Okay. Now, if we want to make the diagram of okay, how do I say this? So what is Ct? Ct earlier, Ct was equal to A negative, but now Ct will be, and we have to write equation for the non-metallic part only, right? So it will be A negative plus HA. A negative is fine as it is, and HA, what we can write? H plus A negative Ka. Okay. If we separate A negative will be Ct Ka Ka plus H plus, and we have to plot in terms of log. So what's going to happen when we plot in terms of log? It will be taking log both the sides. It will be log A negative is equal to log Ct plus log Ka minus log Ka plus H plus. Now, there are three cases to simplify the above equation. So this equation is there. There are three cases to simplify it. Okay. And before going into this equation, we have this HA also, right? So how we can write this HA? HA is simple. Okay. While simplifying the equation, we will see one simple equation for this also. Now, the first case is, case 1 is H plus is too much greater than Ka, which means pH is less than pKa. Okay, what will happen when pH is less than pKa? Log A negative is equal to log Ct minus pKa plus pH. Okay, and second case is when H plus is less than Ka. H plus is less than Ka. In that case, what's going to happen? If we put this H plus is less than Ka, what's going to happen? Log A negative is equal to log Ct plus log Ka minus log Ka, which will eventually give us log A negative is equal to log Ct. So when pH is less than pKa, this equation will go. When pH is greater than pKa, this equation will go. And the third case, pH is equal to pKa, means log H plus is equal to log Ka, which gives us H plus Ha is equal to A negative. So pH is equal to pKa. This happens at equilibrium, which is, so Ha is equal to A negative. So this is equivalence point. Okay. Now we should study about equivalence point. So we need one more equation, right, for H plus HA. So we know that CT is equal to A plus HA, right? Oh no, first we are writing about equivalence point. So CT is equal to H plus HA. Now at equivalence point, what is happening? HA is equal to A plus, right? So this is negative. A negative is equal to HA, which is equal to CT by 2, right? So while putting log on both the sides, log on all the sides, log A negative is equal to log CT minus log 2. So log A negative is equal to log CT minus 0.3. Log value of log 2 is minus 0.3. Okay, this is value of log 2. So what is the uh, significance of equivalence point? At equivalence point, pH is equal to pKa. So at this time, maximum buffering capacity will be there. Something like this. The graph will go like this. So these are the points where there is maximum buffering capacity. Next comes the expression of HA. We have expression for H plus, OH minus. Now we have for A negative. Okay, we got the expression for A negative in all the values, like at less than pH, pKa, at more than pKa, and at equivalence point. Now we need to give the expression of HA. Okay, so case 3 is common for both A plus and HA. Okay, this case will be common. So, and the main equation that we wrote for A negative can also be written for HA. What will be the equation? Log HA is equal to log CT plus log H plus minus log H plus minus Ka. The main equation, like we wrote for A negative, it can also be written for HA. And simply, we have to apply all the cases. Case 1. What was the case 1? pH is so much less than pKa. Here what will happen? Simple. Log HA is equal to log CT. Case 2. When pH is so much greater than pKa, what will happen? Log HA is equal to log CT minus pH minus log Ka. Okay, and the third case will be similar. Third case will be similar. Now we have all this equation and we have to draw the equivalence diagram of all these species. So as I told, first we will draw a square, nice square. This is rough diagram. Then simply, and I will write 0 to 14 because this is versus pH. This is versus pH. So 0 to 14 pH will be there. Next comes, we need to all the CT value. So 0 to minus 14. Now, as I told how to plot H plus and OH, simple. This will be our H plus and this will be our OH. This is H plus and this is OH minus. Now, here comes the trick. First we will plot H plus HA, then we will plot A negative. I will use some other color so it becomes easier. Let's say this point is our, okay, let's first plot pKa. Let this point be pKa. Now, the other thing is, we have seen earlier, right? This concept, log CT minus 0.3. All these concepts we have seen, right? So this is happening where pH is equal to pKa. This is happening, right? Minus 0.3. So I'll tell you where to do that. So 0.3 points this side and 0.3 point the other side. We have to make two more lines. You have to see the derivation only once. After that, you will be able to do it on your own. We have already drawn H plus, we have already drawn OH minus, and now we are drawing the pKa and plus minus values. Now we can plot CT at some point, whatever the CT be. It can be 10 raised to power minus 5, 10 raised to power minus 4, anything. So whatever, if it is minus 5, plot it here. If it is minus 4, plot minus 4 here. Now, when pH was less than pKa in HA, it was equal to CT. Log HA was equal to CT. So we will simply draw the line like this. Okay. Now, there will be, after going to this line, at other point, when the pH was greater than pKa, this thing was followed, right? So at the 45-degree angle, we will go down. So this diagram is for HA. Now what will be for A negative? So when pH was less than pKa, first we will draw pH greater than pKa. Means pH is right side of pKa. So there what will happen? Exactly like straight line we gave for CT, right? Exactly like that we have to give. Now pH, when pH is less than pKa, equation was something like this for the other A negative. Just at 45 degree we have to draw like this. Okay. And this is for A negative. Right? And the point where both the graphs meet is your pKa. Okay, so this is how we can draw the diagram for weak monoprotic acid, equilibrium diagram for weak monoprotic acid. So this was log species and this was pH. And this angle is 45 degree. Okay, similarly, this angle is also 45 degree. So I am drawing it roughly, but when you will draw it in proper graph paper, you will get really good results. And this can be also drawn in Visual Mintech. Okay, coming to the equilibrium diagram of the weak diprotic acid. Also, I was planning to tell you three concepts only. One is equilibrium diagram of strong acid. We have seen it was simple. Let's revise it again. It was very simple. Just a box. This will be H plus, this will be OH minus, and just one whole value of AT. H plus, OH minus, and this A negative. Okay. For weak monoprotic acid, we have seen this one. Now next is weak diprotic acid. So first step, you remember, first we have to write balanced chemical equation. So what will be the balanced chemical equation for diprotic acid? Let's say, let us represent it by H2A. It is weak acid, so that is why we will see reaction in both the direction, right? Ha will also be dissociated. It will be H plus A2 negative. Now you can see, right, we will get many species here. There were three species in monoprotic strong acid. Then monoprotic weak acid, there were four species, and here we will see many more species. So this was the right balanced chemical equation for all the reactions. What was next step? Equilibrium constant. So Ka1 will be equal to H plus Ha upon H2A. Ka2 H plus A2 minus Ha, and Kw, that will always be there, H plus OH minus. Third thing is species identification. The steps will be similar in all kinds of solution. Okay, what will be the species? One will be H plus OH minus, because this is weak, so everything won't be dissociated completely. So that is why we will have many species. So how many this species we have now? 5. So earlier it was 3, then 4, then 5. If we will make it triprotic acid, there will be 6. Now, since it is a weak acid, so Ct will be what? Now we have to write Ct equation, right? It will be H2A, Ha, A2 minus. Now we have to develop the plotting equation. We already have for H plus and OH. right? So for other things, we'll just have to make. So from the equilibrium constant equation, HA negative is Ka1 H2A by H plus, and A2 negative, we have Ka2 HA negative by H plus. Therefore, A2 negative will be Ka1 Ka2 H2A by H plus square. Putting all this thing in CT equation, what we will get? Let's put H2A in common. We will get 1 plus Ka1. This equation looks familiar, right? We have to write the same equation. Okay. Then H2A will be equal to, after solving everything, we will get CT H plus square H plus you don't have to remember the derivation. Just after that, whatever graph we will get, you can draw that, and then you can find pH or the equilibrium or the concentration of any possible compound. And if we take log on both the sides, because equilibrium diagram is what? It is based on log. So we have to take log both the sides. So taking both sides log, and log H plus we will write as pH, all those things. So log H2A will be equal to log CT minus 2pH, because when we will take log of this, it will be 2 log H plus, and log H plus is what? Minus pH. Minus log H plus Ka1 Ka2 plus H plus Ka1. Now here we will get two values, right, of Ka. So if we draw a rough diagram here, we will get one will be Ka1, other will be pKa2. Okay, so now, like we were doing earlier, we were dividing it into segments. So one case was less than pH, pKa more than pH. Other segment was pKa less than pH, and the third case was pKa is equal to pH. But in diprotic case, we can have more. One is pKa1 less than pH but greater than pK2. One less than pKa2 but greater than pKa2. Okay, and between these two, and either equal to Ka1, pKa1, or either equal to Ka2. So we will get total 5 permutations combinations. So 5 cases. Okay, hope you understood. One will be this point, other will be this point, third will be this point, fourth will be exactly this point, fifth will be exactly this point. So like that, we will have 5 cases now. So let's say case 1. Case 1 is Ka2 is less than Ka1, okay, which is less than H plus. So what does this mean? pKa2 is greater than pKa1 and pKa1 is greater than pH. So when we will use this case in this particular equation, what will happen? Log H2A is equal to log Ct minus 2pH minus log H plus square. Okay, and we can write this as 2pH, right? So log H2A is equal to log Ct. So in this pH range, log H2A is equal to log Ct. Okay, what will be the next case? Ka2 is less than pH. Ka2 is less than H plus. So what will happen? pKa2 is greater than pH. It means we are talking about this area, third area. What will happen? The equation, okay, so any term containing Ka2 in the sum of the main equation, so equation, because here Ka2 is very less, so any term containing Ka2 can be neglected in this equation. Okay, so we will get something like this. Log H2A is equal to log Ct minus 2pH minus log H plus square plus H plus Ka1. Okay, so rather than being a straight line, this will be a curve. Okay, and this thing will be applicable in the pH 1 unit either side pKa. So equation will be curve. What that mean is, like we were plotting pKa, right? Like this. So either side of pKa, 1 unit either side of pKa, this equation will be applicable. It will be in the form of curve or something. We will see what kind of curve it will come. Coming to the next case, that is Ka2 is less than H plus, which is less than Ka1. So pKa2 is greater than pH, which is greater than pKa1. So here what we have to do? So here we have to neglect all the H plus and because H plus is very less than Ka, so we have to neglect all the H plus and pKa1 thing. Okay. So what we will get? Log H2A is equal to log Ct minus 2pH minus log H plus plus log Ka1. This can also be written as log H2A is equal to log Ct minus pH plus pKa. So here it is also a straight line because we are not getting any squares. So this is also a straight line. Coming to case 4. Okay, now for case 4 and 5, I will write the condition, then I will directly write the equation. Okay, H plus is less than Ka1. So pH is greater than pKa1. So here we will neglect all the H plus values because H plus is so much less. So all the H plus values we will neglect in the main equation. Then what are we going to get? Log H2A is equal to log Ct minus 2pH minus log Ka1 Ka2 plus H plus Ka1. And here, because we have multiplication of these two values, so this is also a curve, not a straight line. So that will be near the next pKa value. Coming to case 5. Case 5 is H plus is less than Ka2. H plus is less than Ka2. So here we will neglect all the, so pH is greater than pKa2. So here we are going to neglect all the H plus values. Wherever there is H plus, we are going to neglect it. So what is the final equation that we will get? Log H2A is equal to log Ct minus 2pH plus pKa1 plus pKa2. So this is applicable for pH at least 1 unit greater than pKa2. This was the case 5. So this was equation only for H2A, right? We have many more species left. So like that, we have different cases for other species also. For example, so as I told, I am just going to write directly the equation and the main condition. Now we have to write equation for HA also. So just by rearranging all the equation equilibrium constant, this was the main equation, right? HA negative is equal to Ka1 Ct H plus H plus square plus Ka1 Ka2 H plus Ka1. So taking log both the sides, we will get this equation. So just note down this final equation. After that, all the cases will be applied. All the 5 cases, as I told, will be applied here also. But I'll give you directly the equations. One Ka 2 plus H plus Ka A1. Okay, so this will be the final equation. Simple. All the cases pH is at least 1 unit less than pKa, and all 1, 2, 3, 4, 5 cases. So we will get certain equations like case 1, same like last time. We will get final equation that will be log HA is equal to log CT minus pKa A1 plus pH. Case 2, we will get log HA minus is equal to log CT. Case 3, oh, this will be case 3 actually if we match it with the previous cases. Now, case 2, it is under the two lines of the pH, either side of pKa1, right? So, this will be log HA negative is equal to log CT minus pKa1 minus pH minus log H square plus H plus Ka1. So this is a curve. Square is there, right? So this is also a curve. The case 4 will be log HA is equal to log CT minus pKa1 minus pH minus log Ka1 Ka2 plus H plus Ka1. Again curve. Coming to case 5. Case 5, we will get log HA negative is equal to log CT plus pKa2 minus pH. This will be straight line. So these are the plotting equations for HA. Similarly, we need to plot the equations for A2 negative. Many species are there, remember? For the A2 negative, what was the main equation? We can write it as Ka1, Ka2, Ct upon H plus square, Ka1, Ka2 plus H plus Ka1. Taking log both the sides, what we will get? Log A2 negative is equal to, I know this portion is little boring, but yeah, we need to know all the equations. So that's why I'm revising it to you all. Log this will be square bracket only. I am writing it's it as normal bracket, but this will be square bracket. This is concentration, and as I told, This equilibrium diagram is applicable only for the ideal solutions. Hence, we have to take concentration, not activity. So that is the one of the major assumption of equilibrium diagram. Okay, simple. All the cases that we have to give, case 1, case 2, similar cases. Okay, so case 1 equation will be log A2 negative is equal to, if you are unable to note it down, like this video will be shared, then you can easily note it down. And you can get all these values in some good textbook also. I'll see if I can recommend, maybe Benefield you can use. pKa2 plus 2 pH. This is for the case 1. Coming to case 2, pH is within the interval to 1 unit either side of pKa, means in this portion. Okay, log A2 negative is equal to log Ct minus pKa1 minus pKa2 minus log h plus square. We are getting square, means it will be a curve. H plus Ka1. Case 3, similar kinds of equation that we are going to get. So now comes the construction of all the points. Okay, so that is big task. So let's start drawing it. Then we will solve 1 or 2 questions, then it will become easier for you all. I will see if I can get a scale. Let's first draw a nice box, square box. Okay, we know H plus NOH. And like if it is 10 raised to power minus 4, then Ct will be minus 4. So wherever I will write Ct, that will be whatever the molarity that we are going to get for that particular compound. Now for this we have 2 Ka values, right? So let this be pKa1 and this be pKa2. The values near this point will also have some buffering capacity. So let's say 1 unit either side of pKa value will give some different feature. So whatever the curve portion that we were getting mostly is for this particular part. So 1 unit either side. So this is the base that we got it ready. Now first let's solve for H2A. So H2A, if Ct is minus 4, let's mark some Ct here. Let's say this is our Ct value. Okay, so let's just mark this as Ct. So H2A is straight line till this point. H2A straight line. Okay. Till 1 unit before that particular pKa value. After that, there was one curve here, and after curve, it was parallel to this line. After that, there was again a curve, and then it went something like this. So this is how our H2A was working. Let's say now how this HA was changing. So HA similarly CT line only, but between these points it was straight line. Okay, what was the equation here? It was log HA is equal to log CT. So this was the equation here. And this equation, it was always straight line, no curve portion in entire 1, 2, 3, 4, 5 cases, all the cases. So as I told, this is first case, this is second case, this is third, this is fourth, and this is fifth. So our HA was showing non-curve behavior in all the cases. Next comes A2 negative. So A2 negative will be just opposite of H2A. Okay, you can remember like that. So it will be same CT. Here it will be straight line. Then here there will be a slight curve. Then it will be parallel to our OH line. Then there will be a slight curve. Then it will cut this OH line. This will be behavior of our A2 negative line. So this is how we draw for our diprotic weak acid. And actually these 2 points should meet at the pKa. I'm not drawing to scale, so it is not meeting. Here it is meeting. So wherever these 2 points meet, so here what is happening? We can simply say, right, H2A is equal to HA. At pKa 1 only this will happen, right? And here A2 negative is equal to HA. Hence this is pKa2. So this is how we will draw the equilibrium diagram for the acids, for the weak, all kinds of acid, strong acid, weak monoprotic acid, and weak diprotic acid. Similarly, we can draw for triprotic acid. That will give more equations, and that will give us more variables, and we have to draw many of these lines. So we will just solve one question on this concept. So the question is, calculate the, this you can solve with me, calculate the equilibrium pH. So whatever the point that we were getting the cross points, right, that was called equilibrium pH. So equilibrium pH of 0.1 mole nitrous acid. Nitrous acid is what? HNO2. So it is weak monoprotic acid. Okay, and I am giving you pKa also. pK is 3.29. So this can be easily solved on a simple graph, but you can solve it roughly and you can give me some rough value. So pK value is 3.29. So instead of writing all those equations, there is one thing we can do. Okay, I will give you a simple, very basic concept of solving this kind of question. So we have two things to solve, right? If there is any doubt, you can stop me and ask. This is very important concept. You don't have to remember all those graphs and everything. Simply, you can remember the concept. So this is 0.1 molar HNO2, and we know we have to use HNO2 also and H2O also. So HNO2, H2O, two things are there. So let's first write initial stage. Initial stage, when nothing is happening, we have HNO2 and we have H2O. Now, one thing will be, two equilibrium stage will be there. Equilibrium plus 1, you can write like this, and other thing will be equilibrium minus 1, because when we were drawing all these diagrams, this was one unit difference, 1 unit. So that is plus 1 minus 1. So I'll remove this. So in plus stage, what will happen? H2O will convert to H plus. And in minus stage, what will happen? It will convert to OH minus. And HNO2 cannot gain H plus, right? So there is no plus stage. But HNO2 can lose one proton. So what it will become? NO2 minus. Okay? Means H2O can lose a proton, get a proton, so it will become H plus, and it can lose a proton, it can become OH minus. So when I say minus 1, it is losing a proton, and when I say H plus, it is gaining a proton. So, but for HNO2, it cannot gain, it can only lose. So for minus stage, there are two things, and for plus, there is just one thing. So now we need to write the proton balance equation. This plus will be equated to minus. So H plus is equal to minus NO2 negative plus OH minus. Okay, this is what you got. Now we have to, and as I told you, since this is 0.1 molar, what this means? 10 raised to power minus 1 molar. So what will be the CT value? CT will be minus 1. This you remember, right? So now simple, we have to draw the diagram and find the equivalence point. Simply draw a nice square. We know our H plus, we know our OH minus. This is H plus, this is OH minus. Now we have our CT value. So our CT value, and I told you this is 0, this is minus 14, and this will be pH, right? So this is pH, and this will be 14. Now the second thing we need to plot is pKa. What was pKa? 3.29. This is 7. Okay, so pKa will be, this is 7. 3.5 will be this. So this point will be 3.5. So 3.29 will be little bit this side. So let's call it 3.29. And 1 unit either side we have to mark. And we have to find the equivalence point. What will be the equivalence point? Where both the curves H and O2 will be equal to NO2 negative. This is concentration of HNO2 will be equal to concentration of NO2 negative. This is the point we have to find. So we have to find the confluence point of these. So we have seen in the main diagram, right? I'll show you. Yeah. How we are drawing HA means complete acid. We will go straight here. Then we will just make a 45-degree angle to the down. Okay. So similar thing we are going to follow here. First we will mark CT. So CT, let's say -1 here. So let's first draw a CT. This is CT, okay? Now we will make HNO2. So HNO2, HNO2 will be as it is. So it will go straight line here. Then it will take a 90-degree angle. Then it's going to go down. Okay. Now here comes what we need to draw is NO2. So we have seen in the previous diagram how we were drawing A negative. A negative was from this side, from the left side, then 90-degree angle, then it will go down. So how we will draw that? Then 90-degree angle, something, it is not completely 90-degree to the slope, but okay, I'll draw it. I can, let's see. -90-degree like this. Okay. This is how we will draw this. Now you can see this equation, right? H plus is equal to NO2 minus plus OH. Now, how to do this? Just how to calculate this H plus? I will take this color. This line is OH, right? So OH and this was NO2 negative. This was HNO2. So OH, okay, then plus NO2 plus NO2. Now we need to go to H plus. Then we need to reach to H plus. H plus is this line, right? Okay, I'll show you how to go there. Just give me a moment. I need to make this proper. Okay, I lost this point. So we need to balance this equation, right? So H plus is equal to NO2 plus OH minus. So this is OH minus. Here I'll write a different color so it will become easier. OH minus plus NO2 negative, then, and this line is H plus. So we need to cut the H plus line. So wherever it will cut the H plus line, that point is called equivalence point. Okay, H plus is equal to NO2 plus OH minus. So wherever this line will cut H plus line, that point is our equivalence point. So here it is coming less than 3.29. So approximately that is our equivalence point. So the real answer will be pH 2.5. If we will draw it in proper graph, so I will revise it again. We have to make a nice square. We have to make our H plus, OH minus. This is H plus, this is OH minus. Then we have our HA and we have A negative. So in that case, in this case, what we have? HNO2, NO2 negative. First, we will draw our pKa point. Then we will put 1 unit either side of pKa point. Then first, we need to draw our CT. Now, we have to draw HNO2. HNO2 will be up to this point, then 45 degree. How we will draw NO2? From this side it will start. It will be there up to 1 unit right side of pKa. Then it will cut. Okay. Now we need to find the equivalence point. For this particular pH, what will be the equivalence point? It will be nothing. If we look at this proton balance equation, OH plus NO2, wherever it will cut H plus, means sum of right side wherever it will cut sum of left side. So we have OH. We will stop here. Then we have to add NO2. So we will add NO2. NO2 is continuing till this side. Here it is cutting our H plus line. So this point is our equivalence point. So this is how we will solve one more question. Then we'll see. This is difficult question. Okay, let's go for it. Now we need to find the equivalence point of 0.1 molar sodium nitrate, NaNO2. Okay, we have sodium nitrate here. So here there is no H, right? So for that we have to write first step or write balanced chemical equation. So how do we form HNO2? NaNO2, how we will get that? We can get that from HNO2 plus NaOH, and we will get NaNO2 plus H2O. Okay, so NaNO2, whenever salt is given, now you have to do some extra work. H2O is equal to HNO2 plus OH minus plus Na plus. I have just splitted NaOH because that is strong base, right? So it will dissociate completely. So that is why I have splitted NaOH. Now same. At initial stage, what will be there? We will have NO2 minus and we will have H2O. At +1 equilibrium stage, what's going to happen? It will form HNO2 minus, and this is going to form H plus. Here you can start initial stage with uh, see, here we have NaNO2, right? But Na will not do anything. So that is why we will use this NO2 minus only, initial stage. Okay, NaNO2 will not do anything. And in the -1 stage, we have OH minus. Now simple proton balance equation, positive is equal to negative, +1 stage is equal to negative stage. So HNO2 minus plus H plus is equal to OH minus. So here what we will do, we will add these two, and wherever it will cut OH minus, that will be our equivalence point. We have to draw the similar curve. pH is 3.29. Remember from the first question, pKa is 3.29. These are our H plus and OH minus. H plus, OH minus, same pKa value 3.29, 1 unit either side, here, here. Now how we will draw HNO2? And we have our CT value is 0.1 again. CT value is -1. So let this be our CT, -1. Now first we have to draw for HNO2. It will be, let me draw CT somewhere else so that it becomes easier. Let the CT be here, -1. This will be our HNO2, then 45 degree. Then comes our other compound, NO2 minus, NO2 minus here, then 90 degree. Okay, these both are cutting at 3.29. Here comes our this equation. So HNO2 plus H plus is equal to OH minus. So let's start from H plus. I'm coming from H plus. I will mark this equation so it becomes easier. This is HNO2 and this is our NO2 negative. So I'm coming from H plus, then I have to go to, I'm coming from H plus, then I have to go to HNO2. Then I will go, we can spell it. Then I'll go to HNO2 and I will go until I get OH. So here I got OH. This is my OH and this is the pH of the solution. pH is equal to 8. So 0.1 molar NaONO2 is having pH 8. So this is how we solve such kinds of equation. So I have many more questions. I can give 1 or 2 questions to practice. We can do some carbonic acid system also. Okay, let's do one diprotic system. Or let's see some other question. Let's find out the pH of 10 raised to power minus 4 HCl. This is strong acid. Let's do a simple one. Question, let's find out the pH of 10 raised to power minus 4 more HCl. By approximate method, we know what will be the pH because this is strong acid. So there is no Ka value, all those things. But we'll solve by equilibrium diagram. Let's see. So what will be the initial stage? There will be HCl and there will be H2O. Minus 1, plus 1. Plus 1, it will become H plus and HCl won't gain anything. And at minus 1, it may lose 1 proton and become Cl minus. And here it will be OH minus. Let's write proton balance equation. H plus is equal to Cl minus plus OH minus. This is OH minus. And let's simply draw the diagram. This is my H plus, this is my OH minus, H plus, OH minus. And what we learned in strong acid and base. And first here what will be the CT value? CT will be minus 4, right? It is 10 raised to power minus 4. So let's make one CT here, minus 4. Okay, and we studied about strong acid, right? In whole range of pH, CT will be equal to A minus, right? So our A minus will be this whole thing. Means this is Cl negative. Now, just by looking at the equation, Cl negative H plus is equal to Cl negative plus OH. So we'll start from OH, then we'll go to Cl negative and we will go until the point it meets H plus. This point. And this point will be our pH, which is equal to 4 in this case. If we will draw this diagram in a log graph, we will get pH 4 as exact result. So hence we can find the pH of strong acids like this. So this is how we solve such question. Okay. Let's for now let's quickly, I think I'll stop this concept here. Next week we will solve some question of diprotic acid and it will give you time to revise your concepts of equilibrium diagram. Okay, so and the questions for this week that I have prepared, that I will upload in the drive, you can get that. Those questions are very direct, mostly visual Mintek based, so that's why I'm not solving them in class. So that you can do, and I'll stop the session now. If you have any doubt in this equilibrium diagram, please let me know. I'll wait for some time.
Excuse me.
Yes.
So from diagram, it will take too much time for calculation.
Yes, that is the diagram. It's going to take.
Is there any method to find out directly?
Yes.
For pH.
Yes. Absolutely, there is.
No. Okay.
For
So
Huh.
now this question is let find out the pH of 10 to the power minus 4 HCl.
Yes.
That we can find directly pH is equal to 4 na.
4. Yes, correct. Very true. Hmm.
But we are taking this much. He's taking too much time na.
No, no. See, when it is strong acid, you can directly find, right? But there
Okay.
is one method. If I give you 10 raised to power minus 10 raised to power minus 8 HCl, what will be the pH?
Sorry.
If I give you a sample of 10 raised to power minus 8 HCl, what will be the pH?
Hmm. It is less than 7 na. Around
Yes,
6.8
correct,
or
correct.
9.
So just by looking at this, you cannot find. So there are two
Hmm.
methods to solve this question.
Hmm.
Either there is one thing called exact method that will give you pH of something 6.999 after a long calculation, or the other concept is this equilibrium diagram. If you are
Hmm.
able to draw this and solve